Welcome to the AOCS Analytical Division ePoster Pitch competition. We're so excited about our first ever pitch competition and look forward to the student presentations, hearing feedback and questions from our judges and audience. We wish the students well and thanks to our volunteer judges and the audience for attending, listening, and supporting this competition. Here's what will happen today. Each student will present for up to 5 minutes, which may include a visual aid, like a PowerPoint, but not the ePoster, since this would be very challenging to reach on a small screen. Audience who are registered for the meeting, watch the chat area for links to the ePoster found on the AOCS annual meeting website. After each student presents, a 5-minute question and feedback session will occur. Post any questions or comments or congratulatory notes in the chat area. We will try to address as many questions as possible from the judges and the audience during the 5-minute limit. This repeats for every presentation. When all students have presented, we will open an audience poll so that you can vote for your favorite pitch. Please take the time to vote for your favorite pitch. It's time to begin. In the Analytical Division pitch competition, we have 3 pitches from 2 contestants. Our first presenter is Kaavya Rathnakumar from South Dakota State University, and she's currently a PhD student of the Dairy and Food Science Department. She will present on extraction of dairy phospholipids using switchable solvents.
Good morning, and thank you everyone for coming to my presentation. I'm really glad to be part of this AOCS ePoster pitch competition, and I'm really excited to present my work on extracting the valuable phospholipids, which goes as a waste in the dairy manufacturing stream. Phospholipids are naturally present in the milk fat, and during processing, they go into the byproduct. For instance, buttermilk from butter, beta serum from anhydrous milk fat, procream from cheese whey. All these contain an enormous amount of phospholipids. Why these phospholipids are of great importance, especially the milk phospholipids, are considered unique because of the nutritional and health benefits. Consuming these phospholipids helped in reducing cardiovascular disease, cholesterol absorption. In recent times, it is used in the infant formula for the growth and brain development of the infants, and is also used in various processing aids as natural emulsifiers. Since this pandemic, the consumer trends on eating more healthy and nutritious food has come along the way these days, and these byproducts serves this purpose naturally. However, the challenge lies in isolating these phospholipids. Since it is a very wet dilute material, it goes through a multi-step complex procedure since it has to be concentrated, centrifuged, fractionated, which involves a lot of time consuming and also use a lot of chlorinated and flammable solvents, which are injurious to health and is economically unviable. And they use a distillation process, which is also causes various environmental hazards. In order to mitigate these challenges, we came up with a smart alternative is the use of switchable solvents, which is based on reversible reaction of amines. Thus, the change in miscibility. it's from water immiscible. It can switch on and off from water immiscible form to water miscible form by simply bubbling the carbon dioxide. When you remove the carbon dioxide, it goes back to its original form. And the magic lies here. You can reuse the solvent for several extraction processes. From this technique, we were able to obtain 99% of phospholipids from the bottom compared to the traditional methods such as the Falch and the Merjonia method. And it was interesting to note that it was remarkably high yield, like fourfold higher compared to the any other traditional methods as well as techniques which are in existence. In order, however, the extraction efficiency depended on the type of the byproduct utilized in the switchable solvent extraction. So in case of the ultrasound, in case of the beta serum, in order to improve the extraction efficiency of the beta serum, an ultrasound pretreatment was employed prior to the switchable solvent extraction. And from this, we were able to obtain 70% of the phospholipids, which was 10 times higher compared to the beta serum, which was untreated. Further, this was applied into the ice creams, which was not depicted in my poster, which I did later on. And we were able to see 63% of phospholipids in the these phospholipids were mapped at every stage of the ice cream manufacturing process, and we were able to see interesting results in every stage of the processing, which I'll be working on this in future. And these phospholipids helped in converting a low value, this technique helped in converting a low value byproduct to a high value end product. In an economic point of view, this technique is highly beneficial as it is a sustainable and an eco-friendly way to extract the phospholipids from the byproduct source, and you can reuse the solvent, which makes it more sustainable. From this technique, we were able to and generate a higher extraction yield as well compared to any other techniques. And this project helps the dairy farmers in generating income by utilizing single drop of milk, and also it creates more business opportunities to industries by increasing the utilization of the dairy byproducts more effectively. In case of the ice cream, you obtain a converting a low value product to a high value end product, not only enriching it with ice cream with more nutrition, but also it's the phospholipids by itself serve as a natural emulsifier, and which I'll be working on in my future. Thank you.
Thank you, Kaavya. That was a great presentation. Judges, it's time for your feedback and questions. For those in our audience, please add your questions and comments in the chat. Judges, do you have any questions for Kaavya?
I guess I can go first.
Yes.
Great job, Kaavya. That was excellent.
Thank you.
Do you anticipate this approach could be used with other matrices?
So yeah, it can be used. This is a protein matrix. We are trying to disrupt this protein matrix and get the phospholipids. So similar way, it can be used for a carbohydrate matrix as well. It has been already studied, and so if it is so for the protein and carbohydrate matrix, we know it can be done. For other matrices, still studies has to be done to know like what type of switchable solvent will be used.
Okay, great.
I guess I'll jump in if you don't mind, Kaavya. That was a wonderful presentation. I'm very excited about your about your results. I have I guess 2 quick questions. You pointed out that you could reuse the solvent, which I think is a great result. How often do you think you can reuse the solvent, or is there a cap on how frequently you can reuse the solvent?
Okay, so theoretically, it is a reversible reaction, which is based on a Lee-Chatelier principle. So it can be used several times. Like it can switch back and forth several times by simply bubbling the carbon dioxide and removing the carbon dioxide. But however, it depends on the concentration of the lipids, or like the different material concentration, like some other minerals might have in the influence, but we haven't studied that. But theoretically, it can be used like several times.
And does efficiency change as you reuse it?
Yeah, it might change. As I said, it might change depending on the concentration of the products.
Okay. And my other quick question is, how long is this extraction process altogether?
So it is around, it depends, like from 3 hours. We have tried from 3 hours to 18 hours.
Okay. And is like the efficiency or the amount that you're able to extract, does it increase monotonically? Like with more time you extract more? Okay.
So we were when we used a temperature, we were able to obtain high at 60 degrees Celsius with time like 3 hours. But however, it depended on the type. Still more optimization has to be done, and to know like the exact time to get a very high yield. But with 3 hours, we can get a higher yield.
Great.
Kaavya, this is Sneh, and great presentation, quite applied, and congratulations for nice piece of work. My question to you is, one thing which I observed in your results of the phospholipid extract from the buttermilk serum, I feel there is an enrichment of the phosphatidylinositol fraction in your phospholipid extraction and the extract. Do you know why it may be? Is it the nature of the way it is extracted? And then I'll ask my next question once you have opportunity to answer this.
Okay, so yes, so since this phospholipids are present in the outer and the inner membrane, we studied a mechanism study to know like how the switchable solvents interact with the inner membrane and the outer membrane of the phospholipids. This phosphatidylinositol are the enzymes which are present in the inner membrane, and the switchable solvents had an ability to go inside the membrane and extract these phospholipids, which is based on an ion pair formation. And so from that, we were able to know that this linositol was higher concentration of phosphatidylinositol was there, like from our 4 different studies, like all were like the linositol was higher. But however, the presence of sphingomyelin and also other individual components like phosphatidyl ethanolamine, choline were also present, and the distribution was studied using an HPLC, using charge aerosol acid detector, and yes, we were able to get that.
And my last question will be, if that's the case, that the enrichment phosphatidylinositol, and as you told at the onset, the phospholipids concentrated or isolated by this way may be useful as one of the health benefit ingredient. So what do you think will be implication if it is the phosphatidylinositol is enriched?
So as a whole, it has more nutritious benefits, but then we haven't studied the bioactivity, which can be done in future. And also, like we are still working on the ice cream, like what are the individual phospholipids present, quantifying them at each stage of the ice cream manufacturing process, so that will give a more clearer idea on like what type, and also studying the bioactivity. But overall, we know that have like anti-inflammatory properties, other immunological responses, and also it is used in the liposomal production of liposomes. So it's like overall we know that, but still we had to do the bioactivity to know how much it can be obtained from that. Thank you. I think you are mute.
Yeah, thanks a lot. Appreciate it.
Thank you.
Thank you all. Our time is up, and thank you, and well done. The next presenter is Steven Mascrez from the University of Liège, Belgium, and he's currently a PhD student of Jumblo Agrobiotech. He will present on a rapid and efficient method for Dialkyl ketones and Sterols termination in fat.
So hello everyone. So first I would like to thank the AOCS for the possibility to present my work today. So I'm going to talk about the method that we developed to analyze dialkyl ketones and sterols in fat, and to introduce and explain why we analyze dialkyl ketones. I have first to explain you the inter-esterification process. It's a reaction that is mainly used in industries like food or cosmetics field. And this reaction aims to redistribute the fatty acids in the triglycerides. And the aim is to modify the physicochemical properties of the oils or the fats. In this, it exists two main processes. So with enzymes, which is specific and fast, and with chemical reaction, so less specific. But in that case, it means that some byproducts are formed, and this is the dialkyl ketones. And why we decided to develop on the dialkyl ketone, it's a family compound that not so well analyzed. They just for at least method to analyze this and quantify. And consider that there's no regulation on dialkyl ketones, we decided to merge with the sterol analysis, which is really widespread. And as a reference to compare our method, we compare with the International Olive Oil Council for the quantification of the sterols. And this method, especially for the dialkyl ketones one, the use of solvent are huge and it's time consuming. So it's not possible as a routine analysis, and also it's not very green. So our goal was to decrease this, the time and the solvent. So as you can see in material method, we wanted to be more focused on two steps. So the saponification and the purification of the unsaponifiable fraction. So first, the saponification was realized by microwave to save solvent and time. And the heating up is more efficient than the classical boiling. Then a classical liquid-liquid extraction was made to extract the unsaponifiable fraction. And then, so this unsaponifiable fraction were loaded on a SPME. And we separate the fraction of dialkyl ketones and the sterols. So what is important to notice is that the dialkyl ketones are very apolar, so we get this fraction in just 10 ml. And then the sterols. So this method is quite flexible because we can analyze only dialkyl ketones and or the sterols. And then after this, the collection of all these fractions were analyzed in GCFID for the quantification and by GCMS for the identification. And at the beginning, each sample was spiked with two internal standards, one dedicated for the dialkyl ketones and the other one for the sterols. So first, before to talk about dialkyl ketone, I would like to talk about the sterols part to have a comparison of our method with a reference. On the first bar plot, you can see the quantification of sterols, so with the IOC, so our reference, and with two conditions. So we keep the final condition of Mascrez, but we choose two solvents, ethanol and methanol. At the beginning, we wanted to work for sure with ethanol because it's greener than methanol. But during the meanwhile, of course, the COVID situation arrived and the ethanol price blew up. So it was a good occasion to see the impact of the use of solvent between ethanol and methanol on the final extract. And what we can see is generally the quantification is the same. We can see some little differences, but this, especially for the really low compound in the olive oil, and especially this one are eluted close to the higher one, so the beta-cytosterol that can affect the signal of these. And then, so we wanted to also take advantage of the sterol measurement and to see if the interesterification had an impact on the sterol profile of different matrices. And you can see on the two bar plots on figure 4, so for the palm oil and the rapeseed oil, the comparison of the sterols, in one part, one side, non-esterified, and the other part with chemical interestification. And as you can see, we can conclude that there is no effect in that case of the interestification. And then, so for the dialkyl ketones, it was a bit more tricky. Consider that they are not so well analyzed. The library for the match of the different dialkyl ketones are not present in the classic libraries. So what we did is we observe a fragmentation pattern for each dialkyl ketone, depending of the chain length. And the length of the dialkyl ketone depends from the length of the fatty acids present in the matrix and triglycerides, sorry. And then this is how we could identify them. And so to conclude, we succeeded to optimize a flexible method that able to analyze two family compounds, namely dialkyl ketones and sterol. Thank you for your attention, and I'm ready for all your questions. Thank you.
Thank you, Stephen. That was a great job. Judges, it is time for your feedback and questions. For those in our audience, please add your questions and comments in the chat. Judges, do you have any questions for Stephen?
Sure, I can go first. Thank you, Stephen. That was really good. Was the effect of the interesterification on the DAK and the sterols hypothesized, and were the results from the analysis of the real-world samples in alignment with those hypotheses?
So the hypothesis was more for dialkyl ketone, especially that they are a byproduct of the reaction of the interestification with the chemical reactions. And we suppose they are not byproduct from the enzymatic way. We checked and we didn't notice yet some dialkyl ketones. So the interest to analyze dialkyl ketones for the moment can be a good marker of which process we use to verify as a quality control the process used for the samples. And the sterol, we use this opportunity because there's just I think one article in the literature that suppose that the interestification doesn't affect the sterol, so we wanted to confirm, and the results show that there is no impact on the sterol's profile.
Okay, thank you.
Yeah,
Steven,
Steven, I may ask a question
sorry, go
to you.
ahead.
This is Sneh Bhandari.
Sorry.
Go ahead. Go ahead, Arun.
Yes, please go ahead, Sneh.
Arun, are you going or should I go ahead?
You can go ahead.
Okay. Sorry about that. Steven said, yeah, good piece of very interesting work. And yeah, it has a lot of application. And thanks for sharing your comparison with the on the olive oil work. My question is more on the dialkyl ketone. It may be interesting work, and wanted to know whether you had any opportunity to analyze dialkyl ketones by your method in intentionally esterified, maybe industrial or laboratory samples, and whether that can be used, this parameter or your method, can that be used for optimization or just studying the intentional interesterification?
So the proposed way we do that, because I didn't hear that well, just sorry. So
intentional, when you wanted, for example, industrial esterification, interesterification.
Yes.
And this parameter can be used, and that's why I'm quite interested in that, to know whether that can be used to optimize the intentional or industrial or laboratory grade interesterification, and also to know whether the process is complete or not, or what's the stage. So this parameter can be of interest. Thanks.
Exactly. Yeah, it could be a good marker, especially because that we noticed. And maybe there's but if we play with the condition of interesterification, maybe we can reduce the Dialkyl ketones, because I can't assure that with enzyme there's nothing, but on the sample that we analyze, we don't have identified them on the chemical interesterification, but not with the enzyme one. So this can be very interesting to apply also in an industrial way, and then maybe to apply more in the industrial process. Yes.
Thanks a lot. Yeah.
All right, Stephen, I have a question for you as well. I'm Arun from NIST. My question basically, the word rapid means different things to different people in different fields. So I guess, how rapid is your technique in terms of time, and how much more rapid is it than a traditional method?
Yeah, so of course, if we reduce time, especially the part that we gain time, it's for the saponification, because we just use 10 minutes of saponification, so very short. And the usual time with the classical boiling saponification is 20-30 minutes, so we earn a bit of time. But there's the part that we earn a lot of time, especially with the SP, so the purification, because the reference protocol is with TLC, so it's longer time and use more solvent. And here you can have your fraction with a lower amount.
Okay.
But it's still a quite long process, because there's 4 steps to achieve.
Right.
But we try to reduce.
Right, but you're still down to about half the amount of time of traditional. Okay, that's impressive. And yeah, and if you have a chance, you should send me an email with those DAKs that we don't have in the library. I'll try to make sure.
Okay, yeah, for sure.
Awesome. Thank you.
Thank you all. And our time is up, and we can move forward. Our next presenter is also Steven Mascrez. His second pitch will be on multiple-cumulative trapping, non-saturated Headspace, SPME, a powerful tool to increase volatile fingerprints.
So, still me. So thanks again for the opportunity to show another part of my work. So here, among the different techniques for volatiles profiling foods, Headspace solid phase macro extraction is probably the most widely applied, because the main advantages of this technique are that it's solvent-free, easy automation, and the flexibility due to the different solvents available in the market. In this study, we decided to work on complex matrix, namely olive oil, and because SPME is the most used techniques for the sampling olive oil volatiles. And these volatiles are really important for the fingerprinting of different olive oil as authenticity or quality assessment. And to sample these volatiles in olive oil, the DVB CAR PDMS, so the coating the most used for this. And this one, the mechanism of the extraction is adsorption. So in absorption, many competitions may occur between the different compounds. So that it can reduce, especially the extraction of semi-volatile compound or compound with a lower affinity with a phase. And so here we decided to develop a method to improve the extraction of the volatile with the SPME. And so I'm going to talk first about the Sentry. It's the latest Marx autosampler, and the most important novelty inside is the presence of we call cold trap. So it's a sorbent tube inside the autosampler, what can focus all the compounds inside. So I mean, for example, if you want to extract 2, 3, or more times your sample with SPME, between each desorption of the SPME, all the compounds are focused here because it's a refrigerated trap. And then this trap is heated up very fast and then ejected in one shot and one GC analysis. So here, what the angle of our work was to work with the different volume of sample, because we know that we can assume that the pKa intensity is an indicator of the absolute concentration, and then to quantify with SPME, we need to be in non-saturated headspace. And that we know, so what we show here with the figure 1, it's between 0.1 gram and 1.5 gram. We are from a part in non-saturated headspace and the other part with 1.5 in saturated headspace. And 1.5 gram, it's important to notice that is the most common mass of sample used for olive oil. And so here you can see, so you have the chart for 10 and 30 minutes, but we apply here the correlation with a linear and exponential model. And the linear model fits with the sample, the volume with a higher amount, so 1 gram, 1.5 gram, but the exponential model fits with lower amounts, here 0.1 gram. And the reason here, when we do multiple extraction, so not cumulative, there is an exponential decrease of the extraction from the area. So it's normal that when we apply an exponential model, it fits very well. So on the figure 2 first, here you can see a chart. So on the axis, you can see the KOA. KOA is a constant of distribution between octanol and air, so hydrophobic matrix and the air. And then on the y-axis, you can see a ratio between 1.5 gram on 0.1. So it's just to see that how we improve the extraction when we use a higher amount. And what you can see, we improve the extraction with a low KOA. So for the most volatile compound more present in the air, headspace. But when with a higher volume, higher content of sample, there is no effect on the semi-volatile for the most semi-volatile compound, sorry. And so in the second time also to show you the figure 3. So in the same way, on the axis, you can see the KOA. So to show, in a way to show the volatility of the compound, the distribution between the headspace and the hydrophobic matrices, here the olive oil, and the ratio between 3 times 10 minutes on the 30 minutes of extraction. So in both cases, there's 30 minutes of extraction, but here 3 times 10 minutes, so we're focusing in the cold trap. We are more in the first part of the extraction for the more kinetic one. And so there's less competition between compounds. So the lower compounds, the semi-volatiles are more extracted in that case. So there's less competition between compounds. And so to see if there is a use, of course, to improve the extraction of the semi-volatile compound, as a proof of concept, we apply it to different olive oils with different quality of olive oil, so extra virgin, virgin, and lampant. And so you can see on the first heat map, so 0.1 gram for 30 minutes. The discrimination for the classification are not well because the virgin olive oil are much confounding with the extra virgin olive oil. But when we apply the 30 times 10 minutes, 3 times 10 minutes, sorry, consider if it's GC or GC times GC, the classification is really well designed. So you have a part, the extra virgin olive oil, the gray part, then the virgin and the lampant. And this is very, very powerful because the virgin olive oil is never easy to separate because virgin olive oil has intermediate characteristic between extra virgin and lampant oil. So as a conclusion, we demonstrate that the potential to use less amount of sample and to use shorter time of extraction, we can improve to burst even the sensitivity and the quantity of information for each sample. Thanks for your attention, and I'm newly ready for your question. Thanks.
Thank you, Stephen. That was a great presentation. Judges, it's time for your feedback and questions. For those in our audience, please add your questions and comments in the chat. Judges, do you have any questions for Stephen?
Yeah, this is Sneh. Let me go first. Stephen, yeah, it was a great piece of research work. I think your method, it may make it easier to profiling the volatile components of the olive oil and many other compound oils and similar application. So it's a great work. My question to you was, how did the volatile profile of extra virgin olive oil developed by your method compared with what is available already in the literature? And extension of my question is, are there any critical component or critical profile markers which can be used for authentication and quality of the extra virgin olive oil? Thanks.
So it's a good question, but it's difficult to give a direct answer because it depends which purpose we want for extra virgin olive oil, because it depends if we want to do to check the authenticity, so the origin of the different extra virgin olive oil. But then what makes different, it's more in the semi-volatile compound, because regardless the quality of olive oil, for example, there's a lot of hexanal inside, but whatever and this is the higher compound, this doesn't make difference between the different olive oil. That's why the interest of this technique to improve the extraction of the semi-volatiles can make some difference and help to really distinguish the different quality of olive oil, so extra virgin, virgin, and lampant. So that's why it's powerful to really distinguish this part.
Thanks.
Thank you, Stephen. That was really good. Do you anticipate other oil types would behave similarly to this methodology?
But not yet. It can be even. We are working on some other matrices. Actually, we are working on coffee. But I started with olive oil because, as you can notice, on the previous work that I showed before, I work with olive oil. So it's more about this, my PhD topic. So I started with this, and this is an interesting matrix because it's complex. And now on another complex matrices, we are working with coffee. That's also challenging because it's really complex one.
Okay. And one other question, did you consider other SPME fiber phases?
In that case, no, it can be interesting, especially with different similar adsorption compound. Here it was just to use to have a starting point similar to others. This one is the most used SPME fiber for olive oil and volatiles in general. That's why for these purposes with the Headspace, for us it was the better to start with this. After we can imagine for sure with different coatings and different applications, yes.
Okay, thank you.
Hi, Stephen, it's Arun again. I really enjoyed your presentation. I was most interested in your classification results. So you showed that with the 30-minute run, you didn't have good separation between extra virgin and virgin olive oil, but with the 3x10, you had good separation, right?
Yes.
And so my question is there anything in between that gives you the, is there a lowest amount of time that gets you the same separation? Or like the optimal separation?
Sorry?
Or the, that ensures that you get the separation that you're desiring? So instead of doing 3x10, could you
then, because here, okay, it was just to show the strength of this method. For sure, now we are applying this to for sure a more significant sample, so with more extra virgin, with more virgin and volatile compound, because here just a few, but it was to show that it's easier. And this, in that case, also we wanted to show with a lower sample. So here we have 0.1, but the result can be different with one. But here, what can be done in the second time, it's because we can quantify also in one GC analysis with standard for sure, but it's better in one shot we can estimate the quantification of one compound or many.
Okay, great. And so I guess what is the future work in that realm?
But so here with the century, because we are more an instrumental approach. So it's with the coffee, and here it's for the moment we work on brewed coffee, but then to do immersed extraction. So then we can combine Headspace and also in the one analysis, we can imagine many things because this Sentry auto-sampler has many functions and it allows to play a lot with it. Really, it's a very nice auto-sampler, yes.
Great, awesome.
Hi,
Thanks.
Stephen. We have questions from the audience. Here's one. Very nice research. Thank you and well done. Which SPME fiber or polymer combination did you find worked best for these OO volatiles and semi-volatiles? Do you want me to repeat the question?
Yeah, please, can you repeat the question? Sorry.
The question is, which SPME fiber or polymer combination did you find worked best for these OO volatiles and semi-volatiles?
So the choose of the fiber, you mean? Yeah, it's written, which steps you. But this, we were more focused on the application to play with the multiple extraction. So we started with the most common SPME fiber that was used for volatile, so the DDB CAR PDMS, because it was not our purpose for the moment to change the fibers. But this, for sure, for different application, can be nice to see what we can play. Because here, for example, we are with an adsorption extraction process. But why what can happen? What can you have with absorption fiber? This it's another topic. So all the work is preparing. But here it was really to work on the shorter time and lower amount of olive oil. Sorry.
Thank you. We have another question from the audience.
Yes.
Are these 3 extractions from a single vial or 3 separate vials?
It's the same vial. So here we stay with the same in the same vial. Yes. So to really have this to decrease the low amount. So for sure it could be nice. It depends the purpose that we want. But here we really have to have a non-saturated headspace. So with multiple extraction inside, we decrease the amount of volatiles inside to have a better overview and representation of the all compounds inside.
Thank you. Our time is up. Thank you, Stephen, and thank you all the judges.
Perfect. Thanks.
We will open the poll now. 2 contestants in the Analytical Division ePoster page have completed the presentations. The audience poll is now open for about 4 minutes, and we encourage all of you to vote for your favorite page. While you are voting for your favorite page, our judges are assigning scores to the pages. The poll results will count as one judge. We will add the scores from the judges and the poll together to obtain the total score for each page. Our poll is about to close in 3 minutes. If you have not voted yet, please hurry. We are now tallying the scores, and we will be back in a moment. We have our winners ready. The second place is Steve Mascrez from the University of Liège, Belgium. Congratulations.
Congratulations, Steve.
Congratulations.
Thanks.
And our first place winner is Kaavya Rathnakumar from South Dakota State University. Congratulations to both of you. The first place winner receives $200 and the second place winner receives $100. Or both of you will receive a certificate, free 2022 student membership, and recognition in the AOCS newsletters. The competition is funded by the AOCS Foundation. Thank you, judges, and thank the audience. Thank you, the audience. See you at the next ePoster pitch at 9 a.m. Central Time today.
Thanks a lot.